here. Okay, so actually I should have started with interpreting constants. So this is interpretation of function symbols. Where is this R? Oh, this is interpretation of relation symbols. I still have to interpret the constant symbols, but this is obvious. So for each C in C, of course, C interpreted in M is this class. This is well defined from the beginning. So now, let's say I have this M. I have all the interpretations, yes? Rm. So this is. Yes, so at this moment we have an L structure. That was all this work. And now we want to say, obviously it has cardinality at most this, it's a quotient. So okay, and now something I will not show, that it is so now using lemma 1 can be shown but to do that by induction of complexity of formulas, but I didn't define formally what is a formula, never, so I cannot do that. Induction on complexity of formulas that for any L formula, let's say psi x1, xn, and for any constant symbols c1 and cn, if we plug it, it becomes true in this model. If and only if this formula, this sentence is in T. Okay, so this, if we knew how to formally define formulas from less complicated to more complicated, then similar arguments as in claims 1, 2, 3 would show such a thing, but this in particular implies, and now the proof will be finished, kind of, if phi is in T, then already it is true here. So kind of this part is skipped, so it may look at the end. So what I did honestly was constructing the structure, but I didn't do the last part, because that would, as I said, require formalizing all of this concept, what really is a formula, how it is constructed from simpler formulas, and in each level of construction, we would have to show such an if and only if, which would be always kind of trivial, but it would take lots of time. So here it is when
trivial.
But as I was discussing with Özlem in the break, here actually finiteness of formulas matters. If we would allow infinitely many, like disjunction or conjunction, we would need transfinite induction, and this would break on the limit step. So kind of this is the reason the finiteness here, or the compactness works, and unfortunately, okay, we may discuss a bit later how would it break perhaps if we allowed infinite conjunctions. If you are interested. So now Lemma 2 is proved. Okay, so now from any theory like in compactness theorem, we have to make it like this, so the whole proof is not finished. So lemma 3. So now we force this witness property. So you see how to get this strange theory which has a witness property. So if T is finitely satisfiable, yes, but to get these constants, we have to enlarge our language to allow space for these constants. So like language of rings would not be enough. Then there is a bigger language. So like F prime, R prime, C prime, everything is bigger. Actually only constant symbols will be bigger. So this doesn't really formally mean this. It means that all of the sets of RC are bigger, or not smaller, such that now cardinality is actually sorry, I did not make much. Still, I think it should be L here. Just maybe not so. Yeah, the language, especially since it comes like this here. So this is the kappa. So there is this biggish language, and such that T prime contains the previous theory, so kind of each model of T prime can be understood as model of T. And still T prime is finitely satisfiable, but also has the witness property. Okay, so at the cost of enlarging the language, we make a bigger theory from this original one, which has the witness property.
It's the same when you change L by T, right?
Huh?
It must be the same when you change L by T.
Now actually I'm a bit confused. But at the end it should be like this. So okay, so this is definitely the cardinality of set of formulas. As was actually mentioned before, so I think this is the right, all the possible formulas in the language.
Okay, but it's equal to T, cardinality of T plus value 0 by K, I think.
Not necessarily. If L is uncountable and T is very, very small, then not. So this is a safer, this is a safer choice, and I think this is the right choice. Because we really wanted to say really a number of formulas in the language. That's just a number. So I made here, yes, again a mistake. This so doesn't depend on T. This number does not depend on T. Depends only on the language. Okay. So now proof of lemma 3. So what is this new language? So we don't change F and R, but C prime we do. Okay, it's not L prime, sorry, it's an L1. It will be infinite process of new languages. Yeah, so this is how it happens. We take all constants, and for each formula like this, we add a new constant symbol. So it's a formula with one free variable. Yes, so now this was this moment that for all formulas we artificially added constant symbols, but still we have to define this theory, and we have to make sure it is still finitely satisfiable. So T1 this is just what it should say. So T1 is T plus all the sentences from the witness property. So phi, C, phi. So now we should check it is really finitely satisfiable. And note this does not have witness property. It has witness property with respect to formulas from old language. That's why we would have to repeat the process. But of course we will be totally dead if we lose finite satisfiability on the way. So this has to be checked. So proof of claim. Okay, so now again we would have to find some model. So take partial in T1 finite. So T1 comes from T, and it has this new sentences. So let delta 0 be the part coming from capital T, maybe empty, maybe not. Definitely finite. Because it's a subset of something finite. So this has a model. T is finitely satisfiable. So this finite subset of T has a model. So there is L structure M, which is a model of this delta 0, and we want to expand it to make it a model of delta. So now what? So actually we will even, I think, make it model of delta 0 and all the sentences. So for any, okay, so we'll expand M to an L1 structure to make it a model of this. But as I'm saying, I think already it will be model of delta 0 and all of this, in particular of this. So to expand it, we have to find interpretations of all these new constant symbols.
There's a constant.
Yes, sorry.
In the definition of delta 0, you say delta composition T. What is the meaning of delta composition T?
What? There's no
Intersection. The circle didn't become a circle. It's
It is so hard to see in here.
no. This is a circle. Okay. Intersection. Just a part of, as I was saying, a part of this delta is here. So this delta 0. Delta 0 is here, and maybe there is some rest here. Okay. Expand it. So for any L formula psi like this, we need to find a good C phi interpreted in M. So what will it be? So we just look. There are two options. So if it may happen, so now we really give a meaning to it. We give a meaning to this witness property. If there is something to witness, then we pick a witness. If there is nothing to witness, we pick anything. So still nothing very deep, but a little. We cannot do it totally randomly. So if it is true that in M this holds, it means there is some element in M such that phi of this element is true in M. Then we take C phi M such that it is a witness. It really witnesses the truth of this sentence. So finally this witness becomes really a witness. Okay, if this is true, such a thing exists, and we take any of such. If not, then take any, whatever we want. And then you can see that with such a choice, of course, all of these sentences are true. Because if this was not true, then this doesn't matter. Because already the whole sentence is true. If it was true, then we choose the right one. Okay, so by construction, this new, this M with all this phi M, there's all these other possible sentences. So claim is proved. For any finite subset of this new theory, we found a model by finding model of this old part and interpreting these constants that they should be interpreted by the actual witnesses of this part here. Okay, so we have a claim, and now we continue. So T1 is finitely satisfiable, but as I said, it does not have the full witness property. It has witness property with respect to formulas from L. But we can repeat, actually, a bit like in the construction of algebraic closure. In the standard construction, we just add solutions of the base field, and which is actually enough, but we don't know yet. We got some bigger field, which has all the solutions of polynomials of the smaller field. We repeat the construction, and then do it Aleph 0 times, and at the end, we get algebraically closed field, and here it's the same. So now, we do the same to obtain language L2 and T2 of T1 such that T2 and has the witness property with respect to formulas from L1. So of course we continue. So at the end, our L prime is the increasing union, and T prime is the increasing union of the n's, and they all were finitely satisfiable. It witness on the finite part, so this is finitely satisfiable, and then by the construction, it has witness property with respect to the good language. So this is okay. Okay, repeating this process and repeating. So it was not enough to add all these constant once. We had to add them again and again and again. but it was happened countably many times, so the cardinality did not grow over this, because this is number of formulas, and we repeat the process countably many times. Will I finish today? So now the last lemma. This was about getting witness property. Now we have to get maximality. So this is lemma 4. Now we don't have to change the language. So if t is finitely satisfiable, then in the same language there is a bigger theory which is finitely satisfiable and maximal. Tigre, T-star. Contains T. T-star is maximal now. And finitely satisfiable still. Okay, and after this, I will be able to prove compactness theorem. But I will have no time. But this is the moment. Okay, this is slightly interesting moment. So far, I think was there an axiom of choice used? Okay, maybe a bit with these witnesses. But now it will be strong. Here it will be kind of strong usage of axiom of choice to find this maximal one. So this is kind of non-constructive moment of the proof, this lemma 4. As usual, yes, as for example, if you want to find maximal ideal, it's axiom of choice. So it's similar thing here. Okay, so it will be kind of, let us have an L sentence. So now claim our T is finally satisfiable, so I'm saying that like something which is needed to apply Zorn lemma, either this is finitely satisfiable or this is proof of claim. So assume the first one is not finitely satisfiable. Of course, we want to show that the other one is. Okay, so since this is not finitely satisfiable, then there is some finite part of T such that this finite part of T with phi has no model. Yes, because the whole thing is not finitely satisfiable by assumption, such that no L structure is a model. Okay, so what does it mean? It means that for any L structure M, if it satisfies this part, then it cannot satisfy this part. So if M satisfies, if this is a model of delta, then it is not true that M satisfies phi, so M satisfies not phi. Yes, because always one of them is true. But then, okay, now I forgot what's going on. Okay, so this is something which is true. So now we want to show that this is finitely satisfiable. We take a finite subset here, so a finite subset here, and this negation of phi, let's say. Okay, but then, now everything will be combined. This is finite and this is finite. Okay, so then this previous one showing that this is not finitely satisfiable together with the sigma is finite here. T is finitely satisfiable. So there is a model of this part. Okay. But since M in particular is model of delta, M satisfies not phi. And then it satisfies this and this, so that by this part, so we have this, so M satisfies this, and this is arbitrary finite subset of this theory, so it is finitely satisfiable. So this finishes claim. Yes, so I got a bit lost in the middle, but then, yes, if this was not finitely satisfiable, then the other one had to be. And now I am leaving you as an exercise to finish the proof using axiom of choice. So, yes, so that's like typical beginning of application of axiom of choice. You can always go one way out of two, and then axiom of choice tells you you can reach something maximal. problem 9 using claim and Zorn's lemma show lemma 4. So find this maximal one, which is still finitely satisfiable and contains this t by making this. Okay, and this is the part which is highly non-constructive, this maximality. Okay, I guess I can finish compactness theorem surprisingly. So proof of compactness theorem. So we start from the assumptions T is finitely satisfiable. It's kappa. And we want to find model. Yes, we want to find model. There is model of T of cardinality at most kappa. So by lemma 3, yes, as in lemma 3, bigger language, but still, okay, L prime actually is kappa, and T prime containing T finitely satisfiable with witness property. And to this one we apply lemma 4. So now apply lemma 4 to T prime. Okay, so in lemma 4 there was no witness property, but witness property cannot be lost in bigger theory. You can notice easily soon lemma 4 to T prime to get then I think you would lose maximality.
Yes.
Okay, I guess you could continue and make some infinite process, but this is just faster process. I'm not sure, but
I think you're using those lemma. Isn't it enough to order all possibilities?
apparently if you add all, yes, if you use lemma 3 add this witness property, you lose maximality for sure.
Okay, because you are looking maximum for L prime.
Huh?
You are looking for maximum for L prime, basically. Right?
Yes, maximal for L prime, yes. In this part, lemma 4, we don't change language. So, which is maximal and finitely satisfiable. Okay, but this already so prime, this has witness property. It's okay, maybe it's late, but this is totally obvious. Already, all the sentences were in T. So they are in a bigger theory as well. Everything is already witnessed. So now apply lemma 2. Yes, so this T star has all the properties from lemma 2. Okay, as you can see, this kappa was also not lost in this T star process. I I didn't put it here, but the cardinality also didn't change. I should have said, and get, okay, let's say M prime. So it has some more structure, but now, so how this M prime looks like, it has some universe. So very informally I say this is in the language L, and then there is the rest, which is in the language L prime. So if I reduce to this part, it would have to be model of T, because it was contained there. So that's the end of the whole proof. The last thing I may discuss a bit. Okay, maybe it's still. So did you get what I meant at the end? I got a model, but of bigger theory in a bigger language. So I'm saying if I forget about this bigger language part and just think in the old language, this is the model of original theory, which is kind of obvious if you think about it. So maybe I will give an example for this last moment. So this was end of the proof of compactness theorem. So what is the meaning of this last part? Maybe by example. So if L, let's say, is this language of abelian groups, and L prime is this bigger language, then, okay, if I have any sentence, so let's say I have Z normal integers, and here I have some L sentence about groups. So if this is true here, then it's also true in this part. Yes, because he talks only about this.
We can actually minimize.
I mean, it's totally obvious, but yeah.
We can actually minimize the L, right? Because T doesn't have to take everything from L, right? It might be even true if a small part of L. This is like.
No, but I have to. I mean, I have to define a structure which has interpretation of everything from L. So perhaps, okay. So thanks. I think it's a good moment to stop. But questions?